All right, today we're going to pull back the curtain on a little piece of everyday magic. We're talking about the science of making plastic look and feel exactly like solid metal. It's this incredible technology that's pretty much hiding in plain sight. And trust me, the chemistry behind it is way cooler than you might think. So let's just dive right in.
Okay, so take a good look at this. I mean, really look at it. You see that mirror-like shine? You know it's durable. It just screams premium. Every single instinct is telling you that this has to be a solid piece of chrome-plated metal, right? But is it really?
And nope, surprise! It's actually a super lightweight piece of ABS plastic. Now, this isn't some kind of trick. It's a truly brilliant feat of chemistry and engineering. And it brings up a huge question. How on earth do you get a thick, durable layer of real metal to stick to something as fundamentally different as plastic? To really get how they solve this, you first have to appreciate just how massive the problem is. And the problem is, well, plastic and metal are about as different as two materials can possibly be. Trying to get them to bond is basically like trying to mix oil and water. It just doesn't want to happen.
This right here, this really breaks down the core of the conflict. You see, for traditional electroplating, you need electricity to flow through the material you're plating. But plastic is a fantastic insulator. It has zero conductivity. Then there's this thing called surface energy. Metal atoms, they're practically begging to bond with things. Plastic, on the other hand, is chemically lazy. It has really low surface energy, which means it resists bonding. Things just don't want to stick to it.
So that leaves us with two, seemingly impossible hurdles to overcome. We have to somehow make a non-conductive surface conductive, and we have to convince a surface that naturally repels coatings to suddenly welcome them with open arms.
Okay, so let's tackle that first problem, the grip, the adhesion. Scientists figured, hey, if the plastic surface isn't right for the job, well, we'll just have to change it, radically.
The very first step is a process called chemical etching. I want you to imagine using a chemical solution to carve this vast, microscopic landscape of tiny little pits and valleys into what was once a perfectly smooth plastic surface. This isn't just random damage either. It's a super controlled way to create physical anchor points for the metal to literally grab onto.
Now, for decades, this was done using some pretty nasty stuff, mainly highly toxic chromic acid. I mean, it worked, but it was an absolute environmental nightmare. The great news is that science has moved on, and now we have modern methods like chemical vapor treatments that can get the same or even better results with way less impact on the environment. That's a huge step forward.
But modern techniques go even further than just simple roughness. We're now talking about hierarchical micro-nano texturing. Yeah, I know, it's a mouthful, but all it really means is creating roughness on two different scales at the exact same time. Larger macroscopic pits for that mechanical grip, and then even tinier, nanoscale textures inside of them to maximize the surface area.
And this is where it gets really cool, because it shows you where the inspiration comes from. Researchers are literally mimicking nature here. I mean, think about how a gecko can just casually stick to a ceiling. It's not glue, right? It's the result of millions of microscopic structures on its feet. We're applying that exact same principle to make metal stick to plastic. How awesome is that? You know, the Velcro analogy is absolutely perfect here. Those micro textures, they act like the rough, loopy side of Velcro, giving it a really strong physical grip. Then, the nanotextures act like the sticky side, maximizing the surface area for a powerful chemical attraction. You put them together and you get an incredibly strong bond. Okay, so we've solved the grip problem. The metal can now hang on tight, but the plastic is still an insulator. So how in the world do we solve the conductivity issue? Well, the solution is to lay down a conductive foundation, like a seed layer, without using any electricity at all.
This incredibly clever solution is called electroless plating. And instead of trying to force metal onto the surface with electricity, it uses a controlled chemical chain reaction that actually builds a metal layer all by itself. It's pure chemistry, not brute force. It's genius.
So here's how this magic trick works, in 3 basic steps. First, that newly textured plastic gets activated. It's seeded with these microscopic catalytic particles. You can think of them like tiny little magnets. Next, the whole thing goes into a bath that's full of dissolved metal ions, like nickel. And finally, those little catalytic seeds kick off a chain reaction, which causes the nickel to basically fall out of the solution and grow a perfectly uniform, thin metal coating all over the parts, getting into every last nook and cranny.
And just like that, our non-conductive piece of plastic now has a conductive metal skin. It has literally become its own electrode. Now and only now can it go into a traditional electroplating bath to build up those thick, durable, and super shiny layers of copper, nickel, and chrome that we all recognize.
So we've walked through all the mind-bending science. But you might be wondering, why do we go to all this trouble? What are the real-world benefits of giving a simple piece of plastic this metallic superpower?
Oh, the advantages are huge. That metal coating acts like a suit of armor, giving it incredible corrosion and wear resistance. It obviously makes the part conductive, which is absolutely critical for things like shielding the electronics in your phone or laptop. And of course, there's the look, that brilliant mirror-like finish that we all associate with quality and luxury.
And once you know what you're looking for, I promise you, you will see this everywhere, from the grill on your car to the shiny knob on your washing machine. It's in medical devices that have to be durable and easy to sterilize, and it gives that premium feel to luxury goods, all while keeping things lightweight and much more affordable to make.
So what this all really boils down to is getting the absolute best of both worlds. You get the appearance and the tough-as-nails durability of metal, but at a fraction of the weight, at a fraction of the manufacturing cost. It is a true engineering win-win.
And that brings us right back to where we started. Now you know the secret. The next time you grab a shiny metal handle or admire a chrome logo, you'll have a brand new appreciation for the complex science that just might be hiding right beneath the surface.
And, this technology is constantly evolving. It's always moving towards greener, faster, and even more advanced methods. It really makes you wonder, with the ability to give almost any surface to properties of metal, what incredible new applications are just around the corner? What will we coat next?